I'm Maniego. My group mate is Ayroso, and we are about to discuss the isopropanol dehydration via extractive distillation using low transition temperature mixtures as entrainers. In the abstract, low transition temperatures mixtures, or LTTMS, also known as deep eutectic solvents, show properties that make them suitable as entrainers for extractive distillation. Two different low transition temperature mixtures were considered as potential entrainers for the extractive distillation of the isotropic mixture isopropanol plus water. Lactic acid plus choline chloride with a ratio of 2:1 and the glycolic acid plus choline chloride with the ratio of 3:1 were selected for this work. Vapor plus liquid equilibrium measurements of the pseudo-binary systems isopropanol plus LTTM and water plus LTTM were measured at different concentrations of LTTM in a pressure range of 10 to 100 kilopascal. Vapor plus liquid equilibrium data of the pseudo-ternary system isopropanol plus water plus LTTM were also measured at constant pressure 100 kilopascal and constant LTTM and molar fraction of 0.05 and 0.1. It was found that these LTTMs cannot break the isotope at those concentrations. However, the isotope was displaced to a much higher isopropanol concentration. The NRTL model was successfully applied to fit the experimental data. In the introduction, the author first described what is an isopropanol. Isopropanol, or IPA, is a bulk chemical mainly used as solvent or as a chemical intermediate for the production of monoisopropyl amine or isopropyl acetate. Mixtures of IPA and water that need to be dehydrated can be found in the production of IPA by indirect hydrogenation or by fermentation of cellulosic materials, as well as byproducts and many other processes where IPA is involved. The IPA plus water mixture presents an isotope at 87.5 weight by weight percent. Therefore, the IPA dehydration by ordinary distillation is basically impossible. It's impossible. Several alternative dehydration processes have been reported: isotropic distillation, evaporation, liquid plus liquid extraction, reactive distillation, adsorption, and extractive distillation. In this experiment, the researchers used extractive distillation. So what is an extractive distillation? Extractive distillation is distillation in the presence of a separation agent called an entrainer, which interacts differently with the components of the original mixture and therefore alters their relative volatilities. The main characteristics of a separation agent are: first, higher boiling temperature than the components of the original mixture; second, miscibility with the mixture, recyclability, low toxicity, and biodegradability. Different salts and ionic liquids were reported to be feasible separation agents in the extractive distillation of the IPA plus water temperature. However, the main drawbacks for the large-scale application are their price, the complexity of the synthesis, and the amount of separation agents required. Low transition temperatures mixtures are discovered in 2003. Seem to be a promising alternative to ILS because they share many of their properties, but they can be prepared more easily and cheaply. Originally, LTTMs were called deep eutectic solvents, or DES, but this name does not cover the complete class of solvents because many measures do not show the technique melting point but the glass transition indeed. Instead, the target of this work is to determine if LTTMs can be used as entrainers in the separation of the isotropic mixture, IPA plus water, via extractive distillation. In order to demonstrate that vapor plus liquid equilibrium VLE data of the corresponding pseudo-binary and pseudo-ternary systems were measured, where the LTTM was treated as a single component. 2 LTTMs were selected with this purpose. The first one is the glycolic acid plus choline chloride with a molar ratio of 3:1. Second, lactic acid plus choline chloride with a molar ratio of 2:1, LC 2:1, and like that. Both LTTMs were used as entrainers. Structures of the LTTMs are illustrated in the table 1, and I'll be showing that later. Wala pa naman. The RTL model was used to fit the experimental data. Also, during the RTL fitting, the LTTMs were treated as a single compound. We proceed to the methodology or the experimental. First, what are the materials used? The chemicals used were of the high purity and purchased from the trustful sources. They are shown in the table 2. As you may see, we have the isopropanol with a 98% purity, glycolic acid with a 99% purity, the lactic acid with 99% purity, and the choline chloride with a 98% purity. The ionized milliliq water content was studied in all studied mixtures. The water content was measured by using Carl Fisher moisture analysis, type Metrotron 795. The water content was between 0.4 and 0.7% weight in all cases. The LTTMs preparation. LTTMs were prepared by following procedure already reported. Mixtures were prepared using a Mettler AX205 balance with a precision of plus or minus 0.02 mg. Both HBD and HBA were added to a flask and heated while stirring. Thus, the uncertainty in the molar mixing ratio is plus or minus 2%. This is based on the uncertainty of the balance reading and the purity of the constituents used. The temperature was controlled using a thermostatic bath with a temperature controller IKA ETS D5. GC 3:1 was prepared at 343.15 Kelvin, while LC 2:1 with a molar ratio of 2:1 was produced at 333.8 Kelvin. Now, the VLE determination. Experimental VLE data were obtained using an all-class volumeter. Pressure and equilibrium temperature were determined with an accuracy of plus or minus 0.1 kilopascal and plus or minus 0.5 Kelvin. All solutions were prepared gravimetrically by an electronic balance, meter Toledo AX205, with a readability of plus or minus 10 raised to negative 4 grams. For the VLE measurements of the pseudo-ternary after the equilibrium was reached, a sample of the vapor pressure and a sample of the liquid phases were taken. Then, a certain amount of the system was removed and a new mixture of IPA plus LTTM and water plus LTTM was added, keeping the LTTM concentration constant. The composition of the condensed vapor phase, IPA plus water, was analyzed using a variant CP3800 gas chromatograph GC equipped with a flame ionization detector and a variant CP-SIL5CV column. The GC methods is described. No presence of entrainer was detected in the vapor phase. In the liquid phase, the IPA mole fraction was determined using the same GC method, where the low volatile LTTM was captured in the liner place before the column, while the water content was analyzed using Carl Fisher moisture analysis type Metrom 795. The LTTM concentration was determined via mass balance calculation. Next is the result and discussion and the conclusion. Those parts will be discussed by my groupmate Timothy Ayroso.